Hi, my name is Pablo, and I'm presenting eSR, Super Resolution for the Masses. Image upscaling is implemented in almost all display devices, and display devices are everywhere. In gigantic wall displays, TVs, computers, phones, etc. The most typical upscaling technique in these devices is bicubic, which is a one-layer transposed convolution with stride. This is implemented efficiently by splitting the upscaling filter into several channels and then mooks them out in a single image by using a pixel shuffle as shown here. But we can do better if we use some prior information, and this leads us into super resolution. By no surprise, the leading techniques in image super resolution today use deep learning. These two here, fast SRCNN and ESPCN, are some of the smallest systems that we can deploy on edge devices. Note that we have multiple convolutional layers with multiple channels. Our plan is to reduce the computations into a single convolutional layer. The simplest decision we can take with C candidate upscalers is to choose quickly by taking the maximum value here. And this is actually equivalent to a max out network by Goodfellow and others. Okay, this is fast, but it's a bit desperate and missing basic principles. So can we do better? Let's take a look at one of the oldest ideas in super resolution. We first define patterns, for example, edges, estimate the probability of having one of these patterns. Here we can use template matching, and then compute the expected output of these candidate upscalers. This is just a weighting average. Template matching uses filters with the shape of the pattern, and upscaling filters follow a similar shape. Both matching and upscaling filters can be part of one convolutional layer, as shown here. C channels go to a softmax and estimate the probabilities. And these are used to compute the expected value. As you can see, we end up with a self-attention model. We try other two variations. First, we split the matching filters into query and key filters to make it equivalent to the self-attention in transformers. And we also tried multiple layers before the template matching to better compare against ESPCN. We trained more than 1,000 model configurations under identical conditions. We tested speed, image quality, and power consumption, among others. One of the most important observations appears here for 2 times upscaling. We plot speed versus PSNR, and most systems can beat bicubic, and we see a clear trade-off pattern. Each model must sacrifice quality in order to gain speed, but the curve is quite different for one-layer models. For high quality, deep learning rules, but deep learning methods fail miserably when they try to run faster. And here, one-layer models behave much better. So depending on the hardware, we can now choose our best upscaler. Finally, we can take a look inside the template matching system. We do not observe the smooth and directional filters I showed before. But, instead, we see independent subpixel processing, leading to some checkerboard patterns inside the system. This is after training with a simple L2 loss that ignores our template matching ideas. Okay, so the filters are not smooth, but are they at least similar between matching and upscaling? It is difficult to say from these images, so we computed Pearson correlations. And here we observe, especially for 2 times factor, dominant correlations along the diagonal. So these systems are leaning towards template matching, and it seems easier for small upscaling factors. Okay, thank you very much for listening, and please check our paper and supplementary material. We hope you find it useful. Cheers.